So let's start with the last thing that we need to know about cosets for now. This lecture is on the concept of normal subgroups, and this will be of moderate importance for us this semester, but it's going to be really important in the fall if you take Math 432. But this is really just a fact about cosets within a group, and so since we're doing that now, I think now's the time to learn it. So let's begin. For this lecture, there won't be any associated Canvas quiz because there aren't any good questions I can ask you for Canvas, but it will feature on some future homeworks and exams, okay? So we do need to learn this stuff. If you have any questions about it, just post them to the discussion board. So anyway, as we've seen, when you choose a subgroup H of a mother group G, you get a left coset partitioning of G, right? So they partition, the cosets all partition your group without overlap. But of course, there's also the corresponding right coset story. The same thing happens on the right side with right cosets. And these two different partitionings of the mother group have really nice properties when the chosen subgroup is nice, and that means normal. And so our goal in this lecture is to describe what a normal subgroup is, okay? In order to do that, we need a piece of auxiliary terminology, and that's the terminology on conjugates and conjugation. So here's the first definition. Let G be a group and take any two elements you like, X and Y, from your group. The conjugate of X by Y is this element right here. You sandwich X within Y and Y inverse. Okay, so that's the conjugate of X by Y. So it's always a conjugate of the middle guy by the outer guys. And on the outer guys, the inverse occurs on the right-hand side. Okay, some authors define conjugation as Y inverse YX. I'm sorry, Y inverse XY, and that doesn't matter. But for us, we'll conjugate YX, Y inverse. Okay? So as an example, suppose you're in G being D4, the dihedral group of order 8. Then the conjugate of the vertical flip by R90 puts the of part, the vertical flip, within R90 and R90 inverse, which is, of course, R90, FV, R270. If you just read the Cayley table and do the math, you get that this is the horizontal flip. So the conjugate of FV by R90, the verdict is, the answer is FH. Now, the conjugate of R90 by FV, so I've changed the order of my terminology here. Note that I'm now conjugating R90 by FV, not the vice versa. Would be this term, would be R90 in the middle, sandwiched by FV and FV inverse, right? And FV is its own inverse, so it's this, and so if you just do the math, you get R270, okay? For another example, in the symmetric group S3, the conjugate of sigma 2 by sigma 4 is this element, sigma 4, sigma 2, sigma 4 inverse. And if you do the math, you get this is sigma 6. Okay? So conjugation is a really important property in advanced group theory. But for us, we really only care because it helps us to define normality of subgroups. This is the key term of the day. Okay? So suppose you have H is any old subgroup of G. Okay? H is special. It gets promoted to being called normal. Okay? So we say H is a normal subgroup if H is itself closed under all possible conjugations from G. Okay? In other words, when is H a normal subgroup? Well, when you take anybody in H, that's the middle term of the sandwich, and then you take any element of G, even the ones that are outside of H, and you conjugate by those guys, the resulting conjugate, for some reason, lands back inside of H and nowhere else. Okay? So it's a really, really strong property because you're asking that every element from H has a conjugate by every element of the parent group that somehow lives back in H. That's what normal means, and you'll see why you care in a little bit. For now, let me keep the definition on the screen here, and then we'll look at these two examples. So here's a subgroup, a little tiny subgroup of order 2, sigma 1, sigma 2, inside of the symmetric group S3. Okay? If you conjugate sigma 2 by sigma 3, you get sigma 3, sigma 2, sigma 3 inverse, and sigma 3 is its own inverse. And if you do the math, you get sigma 6. But sigma 6 is not in H, right? That's not in H. And so this subgroup is a fine subgroup, but it is not normal, okay? So this is not a normal subgroup of S3. Okay? Example 4. Let's stay in S3, but let's look at this subgroup, which is sigma 1, sigma 4, sigma 5. Okay? It's true that this is normal. Okay, this is normal, but it's annoying to check. And let's think about why it's annoying. You've got to check that each one of these elements is closed under all the conjugations from S3. Okay? But there are 6 elements in S3 you can conjugate by. So you got to check that this one, sigma 1, is closed under 6 conjugates. You got to check that this one, sigma 4, is closed under 6 conjugates. You got to check that this one, sigma 5, is closed under 6 conjugates. So in all, that's 18 calculations you have to check and make sure that all those 18 things land in H again. So all 18 verdicts are either sigma 1, 4, or 5. That's annoying. You can do it, but it turns out to be right, and therefore H is normal. So hang on to this example because we're going to come back to it at the end. Okay? So next, I'll let you read this is a collection of simple facts about normality. Okay? So proposition 1 says, let G be a group. The trivial subgroup is always normal. It's not interesting. Okay? So the smallest subgroup is always normal. On the other hand, the largest subgroup, G itself, is always normal. These are not interesting examples. Something moderately more interesting is that if G is a billion, then every subgroup is normal. So in an abelian mother, normality is not interesting because every subgroup is normal. Okay. Now the third one's worth talking about. It's true. Suppose that G is a billion now, and let H be any subgroup. My job is to prove that H is normal. Okay, which means I got to check all conjugations of H by G. Okay. Well, here's what a typical conjugate looks like. I take H from H, I take little g from G, and I conjugate it. But remember that this is in G, and that's abelian, so I can switch these two terms here. And when I switch them, the GG inverse cancels, and I get H. Well, that certainly lives in H, and so every conjugate lives in H, and so it's normal. Okay? So normality is not interesting inside of abelian parents. Okay? So finally, here's why we care, right? Why do we care about normality? Because when H is normal, the left cosets and the right cosets always agree. Okay? That's pretty strong. Okay? So it turns out that when H is normal, every left coset, GH, is equal to the same right coset with the same tag little g. But it's also amazing is that this is if and only if. So the converse is true. So if every left coset is identical to its corresponding right coset, then H has to be normal. It's actually if and only if. I'll let you read the proof. It's only 2 short paragraphs. But this is honestly why we care about normality. A subgroup is normal. A subgroup is normal if and only if the left and the right cosets agree with each other. And that's why we care. Okay? So let's look back at example 4. Example 4, we talked about how this little subgroup was normal, and that would require, unfortunately, 18 different calculations. Okay? Actually, no, it doesn't. So what if we take the subgroup H and work out the left cosets? Well, we've done this before in examples. You know how to work out the left cosets. There must be 2 of them because this is a group of order 6. H has order 3, so it's index 2. So there's only 2 cosets. If you work them out, one coset, of course, is H itself. The other coset is sigma 2H, which is this guy that has sigma 263 in it. So now stop, reorganize your mind, and do the right cosets. Okay? Well, of course, H is also a right coset. Another right coset would be H sigma 2, which is sigma 2, 3, and 6. And notice that the cosets are identical. Here's a coset, and there it is again on the right. Here's a coset, 263. Here it is again on the right, 263, because sets, remember, do not care about order. So the left and right cosets agree. Well, that means that H is normal by proposition. So we're done. We now know that H is normal. This is much easier than checking all possible conjugations. Okay, I'll let you do the same thing, but a similar argument shows that the rotation subgroup is normal in D4. Okay, but this subgroup, R0FV, is not normal in D4. You can use example 1 to see this failed to be closed under all conjugates. Okay, so we got one last thing to say about normality, which is here is a simple test to tell if a subgroup is normal. It is not necessary, but it is sufficient. It turns out that any subgroup of index 2 must be normal. This is very, very, very nice. Okay. So if your subgroup, if you're lucky enough that your subgroup has index 2, then it must be normal. It's very easy to check. So let's prove this quite quickly. So suppose you have a subgroup of index 2. Well, that means there's only 2 cosets, right? There's only 2 left cosets. Right? Well, one of them has to be H itself, right? H is always a coset, which means there's only one other coset, and that other coset must be everything else, the complement of H. So there's only 2 left cosets, right? One of them is H. The other left coset has no choice but to be the leftovers, the complement of H. So here is the complete set of left cosets, H and the complement, the things that are not in H. So now you stop and you redo the same argument with right cosets. There's only 2 right cosets, right? The index is 2, but one of them must be H. Well, since one of the right cosets is H, the other right coset must be the complement. Well, that's the same list you had up here. So the left and right cosets agree, and therefore H is normal. Okay? So the way I remember this is any subgroup that's half the size of the parent has to be normal. That's what index 2 means. Right? So in example 7 here, this tells you that the Klein 4 group, which is these 2 rotations, R0 and 80, and the vertical and horizontal flips. We've seen this as a subgroup already of D4, but now we know it's normal. This is a normal subgroup, even though D4 is not abelian. And that's because the index is 2. D4 has order 8. The Klein 4 group has order 4. 8 over 4 is 2, so the index is 2. And so this proposition says, oh, aha, we got it. If the subgroup is index 2, it must be normal. So this is a normal subgroup. And please note that the same example handles example 4 the exact same way. It was index 2, so we know that it's normal. And that takes care of it. But please remember that is sufficient, but it's not necessary. There can be normal subgroups that are not index 2. Be careful and take care.